Have you ever wondered how a small bullet can do more damage than a big slow truck? The answer lies in momentum. In this lesson, we're kicking off a key chapter in physics, which is momentum and impulse, where we will be exploring how forces act over time and what really happens during collisions. So, in this lesson, basically, we're going to be defining and looking at the formula of momentum and what is an impulse and how is it linked to Newton's second law of motion, and the Newton's second law written in terms of momentum of change, the difference between elastic and inelastic collisions. Those are the two types of collisions we're going to be looking at. Right, so let's begin. So the key important thing we have to know is what is momentum. Now this is basically important because if you don't understand what is momentum, then how are you going to be actually able to apply the formulas of momentum, right? So momentum is basically defined as the product of the object's mass and velocity. So basically it consists of the what? Of the mass and what? And the velocity. So those are the two things that momentum has. It consists of the mass and velocity. So basically this means the formula has to have what? Mass and velocity. And yes, the formula of momentum, it's P is equals to mv, right? Which is the momentum. Now, since this is the formula that can be used to calculate the momentum of an object, there's one important thing that we ourselves have to note. Momentum is a vector quantity. Let me write it here. Momentum itself, it's a vector quantity. Now, one may be asking, why is it a vector quantity, sir? The reason is because it has velocity. And velocity itself is a vector because it has a direction. It acts at the direction. So this means whenever you're calculating momentum, you have to also state in which direction is that momentum applied, which is mainly important. Students usually make a mistake and they tend to forget the direction. And they don't always get full marks because of the silly mistakes. Now, that is all for momentum, the first part, which is this one here. So momentum itself, just to give a recap, it's defined as the object's mass and velocity. The formula of momentum is P is equal to mv, and I forgot one important thing, unit. The unit of it is kilograms per meter second. This is the unit for momentum. And lastly, momentum is a vector quantity, meaning that it has a what? It has a direction. And what? It's important to not forget that direction. And this units basically just show us that momentum is made up of mass times velocity because of the kilogram and meters per second. Right, now let's come to the change in momentum. Change in momentum. What is happening? Now, for this one may say, isn't it the same thing? It is. But this one, it is applied when an object accelerates. Now, if an object is accelerating, this means that its velocity will change. Now, if the object's velocity is changing, then its momentum will also change. That's why we say changing momentum. And how is it defined? The main thing that only changes here is that there's a change in the velocity due to this acceleration of the object. That's the only thing that you need to know. Now you can write it like this or like this, right? Or P final minus P initial, change in P. You're more than welcome to write it in any way that you like. Change in momentum, right? So it's important to understand that this one is applied when there's a change in velocity, meaning that it's accelerating, right? Yes. So, and there's one part that we have to not forget is the linear momentum theory, right? That states that the total amount of the sum of momentum on this side or before it's equal to the total amount of momentum after. We have to not forget this one. This one it applies when there are two objects. If there are two objects, for instance, object 1 which is A and object B which is B, A and B, right? Objects, let me write here, right? So the objects are A and B. So how am I going to calculate the momentum of these two objects? Now, in order for you to calculate it, you just have to sum both of the momentums of those two objects before and after. So basically, you're going to say ma, or the mass of A, times its velocity, of which the initial velocity, and the mass of B times um, initial velocity, it's equals to the mass of A times the V final plus the mass of B and the V final, right? Now, in most cases, the after can result in a collision, of which that one we're going to cover it at a later time, at the end of the video particularly. Right. So, if it comes to a point of a collision, or they stick to each other, this means the two objects will have the same VF, but the masses will be the same. Will be different. That's what I mean. Please remember that the masses will be different because some students tend to make a mistake at that point and they take the two masses to be the same just because the velocities are the same. Right. Now I want us to look at something which is the Newton's second law of motion in terms of momentum. Now for this one I'm going to utilize this. Let me erase here first. Right. Okay. Good. Now, for the Newton's second law in terms of momentum, it's defined as follows. The resultant net force acting on an object is equal to the rate of change of the object in the direction of the resultant. I repeat again. The resultant or net force acting on an object is equal to the rate of change of the object in the direction of the net force. Now, that's how it's defined. And we're going to dig more into it when we're doing impulse. It's because impulse and Newton's second law of motion in terms of momentum, they're related, right? So you have to understand that. Yeah. So let's move on. So far I have covered important things like the principle of conservation of linear momentum, which is the one that I was talking about, of the sum of momentum before and it's equals to the sum of momentum after. That's the principle linear conservation of momentum. It's important to understand it because it will help you in case of two objects that are moving and then they collide with each other and they require you to find the momentum before and the momentum after. Right? So let's look at an impulse. Now, an impulse itself, what is an impulse? Right? An impulse, it's the product of the resultant net force acting on an object and the time the resultant net force acts on the object. That's the definition of an impulse. Now, remember when I said Newton's second law is closely related to um, impulse. It's because, remember, it's because of this, right? It's because of F net. It's equals to change in P over change in T. Now, the thing that I wanted to state before I cut myself, I interrupted myself. It's this. Remember the definition of Newton's second law in terms of momentum stated that the resultant force acting on an object is equal to the rate of change of momentum of the object in the direction of the resultant force. Now, this is the change in momentum of the object in the direction of the resultant force. So that's basically what it meant. So, in simple terms, this is basically the Newton's second law in momentum. Now, what is impulse? Impulse, it's defined, or its formula is a change in P is equals to F net multiplied by change in T. And its unit is newtons per second. And this one we already know it's newtons. So we have already defined the two of them, and we now know what is an impulse. We now know what is the Newton's second law in momentum. The formulas of these two terms. Now I want us to talk about the collisions since we're reaching the end. Right? We're done with this. We're done with this, and we're done with this. Now there are two types of collisions that we have to know: elastic collisions and inelastic collisions. Now, elastic collisions are the type of collisions whereby the energy is conserved and no energy is lost, right? And then the inelastic collision is the type in which the energy is lost. Here's what I mean. So, using the principle of conservation of linear momentum, I know that the sum of momentums before it's equals to the sum of momentum after, right? That's how it is. Now, in an elastic collisions case, both of the sides are equal, right? Both of these sides are equal. By both of these sides, I am referring to the energy, right? The energy in between the two, right? They're equal to each other. But if it's an inelastic collision, the before and the after will not be equal. And for those who are confused, please don't worry. I was just writing the before and after and showing the correlation between the sum of momentum before and after, and the EK before and after, right? Please don't get confused by the EK. And yeah, it's just I'm trying to outline something important right here. So that's all there is to this. You have to know that the elastic collision, the kinetic energy is the same for the before and the after, right? But this does not necessarily mean the momentum, or let's say, if you're going to find if you're given the total mass, the total momentum before, it has to be equal to the total momentum after. That's not the case most of the time, but then yeah, just keep it to yourself that the EK before and the EK after in a elastic collision are the same, and they have to be the same. And then in an elastic collision, the EK before and after, they're not the same. So just like that, you have solved it. So for here, the units are joules. We focus on the joules. And the definition of the elastic collision is as follows. It's a collision during which kinetic energy is the same, like I said. EK before it's equal to the EK after. Whereas inelastic collision is a type of a collision where the kinetic energy is not the same. So meaning a car can collide with another car and lose its energy. In that case, this means this is an elastic collision. So just to bring this to some real life perspective, take this into note. Imagine a car. This is the car. I'm not a good thrower, by the way. Imagine a car hitting the wall. Immediately as it hits the wall, you're going to hear what? Sound. Now that tells you that some of the energy, or not actually some, but the energy of the car, the kinetic energy of the car initially was lost due to the wall, right? But in most cases, you may find the car bashing inside of the wall or bashing through the wall and still moving, but it won't be faster like it was before. So that's all there is to these two terms of elastic collision and inelastic collision, right? So even if we look at all of the other terms um, of momentum, I've defined them all. I've defined them all. So just like that, I'm going to end it off here and hope that you enjoy this one.